Hello and welcome to G Fun Facts Online, the show where we dive deep into the science behind the spectacle. Today, we're looking up at the night sky, at one of its most dramatic and fleeting events, the meteor fireball. Imagine it, a sudden, brilliant streak of light, brighter than any star or planet, tearing across the darkness in a silent, fiery display. It's over in seconds, but that brief moment is the finale of an incredible journey. A story that begins billions of years ago and millions of kilometers away. This isn't just a shooting star on steroids. It's a direct message from the dawn of our solar system, and today, we're going to decode it. The story of a meteor fireball is a tale of cosmic origins, extreme physics, and scientific discovery that gives us a direct line to the ancient building blocks of our world. Before it becomes that brilliant fireball, it's a meteoroid, a silent wanderer in the cold void of space. These aren't just random rocks, they are relics. Fragments of asteroids from the main belt between Mars and Jupiter, dusty debris left in the wake of comets, and even chunks of rock blasted off the surface of the Moon or Mars by ancient impacts. They range in size from tiny grains of dust to objects as large as a small car or a house. And they are moving at speeds that are almost impossible to comprehend, anywhere from 25,000 to a staggering 160,000 miles per hour. That's fast enough to cross the United States from coast to coast in just a few minutes. Most of the time, these encounters are random. A lone meteoroid, on its eons-long orbit around the Sun, just happens to cross paths with Earth. We call these sporadic meteors. But sometimes, we get a real show. At certain times of the year, Earth's orbit takes us through a dense trail of cosmic dust and debris left behind by a comet. This is what creates a meteor shower. When you watch the famous Perseids in August, you're seeing the remnants of the comet Swift-Tuttle burning up in our atmosphere. They all seem to come from one point in the sky, called the radiant, which, for the Perseids, is in the constellation Perseus. But whether it's a lone traveler or part of a swarm, the real drama begins when it hits our atmosphere. The transition from a cold, silent rock to a blazing fireball happens at an altitude of about 80 to 130 kilometers up, far above the clouds. At hypersonic speeds, the meteoroid slams into air molecules. It's not burning in the traditional sense, like wood in a fire. Instead, it's the incredible friction and compression that generates a mind-boggling amount of heat. In front of the meteoroid, a powerful bow shock forms. The air is compressed so violently that it heats up to thousands of degrees, becoming a glowing plasma. This intense heat, along with the vaporization of the meteoroid's own surface, is what produces the brilliant light we see. This process of the meteoroid surface being vaporized away layer by layer is called ablation. It's an incredibly efficient way to shed energy and heat. In fact, the engineers who designed the heat shields for the early Apollo missions and space shuttles mimicked this very process. The ablative heat shield was designed to burn away, carrying the deadly heat of re-entry with it and protecting the astronauts inside. Our atmosphere's ability to ablate incoming meteoroids is our planet's own natural heat shield. Without it, we'd be pelted by a constant barrage of space rocks. Now, any glowing streak is a meteor, but to earn the title of fireball, it has to be exceptionally bright. The official definition says it must be brighter than the planet Venus, which is usually the brightest object in the night sky besides the Moon. These spectacular events are typically caused by objects larger than a meter across. You might be surprised to learn that thousands of fireballs happen in our atmosphere every single day. The vast majority go completely unnoticed, either because they happen over the empty ocean, over uninhabited land, or during the day. To be seen in daylight, a fireball has to be truly spectacular. One of the most fascinating aspects of a fireball is its color. They aren't just white streaks. Observers report vibrant greens, yellows, reds, and blues. And these colors are not random. They are the chemical fingerprints of the meteoroid itself. The intense heat vaporizes the rock, and the atoms of different elements get energized or excited. As they return to their normal state, they release that energy as light of a very specific color. It's the same principle behind a neon sign. By analyzing this light with an instrument called a spectroscope, scientists can figure out what the meteoroid was made of without ever touching it. For example, a bright orange-yellow flash means the presence of sodium, the same element in table salt. Iron also contributes a yellow color. A brilliant blue-green hue points to magnesium. Calcium can add a touch of violet, while nickel glows green. Even the atmosphere gets in on the act. Superheated nitrogen and oxygen molecules can produce a reddish glow. The speed of the meteoroid also matters. Faster meteors have more energy, leading to more intense heating and ionization of the air, which often results in bluer, more violet colors. Slower meteors are more likely to display the red and orange colors of their own vaporizing minerals. So when you see a colorful fireball, you're literally watching a cosmic chemistry experiment unfold in real time. As the meteoroid plummets deeper, the forces acting on it become immense. The pressure of the compressed air in front of it is enormous, while there's a near vacuum behind it. For larger objects, this stress can become too much for the rock to handle. It shatters. This fragmentation is a critical and often the most dramatic part of the fireball's life. Sometimes it's a gradual shedding of small pieces, but for bigger objects, the breakup can be catastrophically violent. A bright, terminal flash, an event technically known as a bolide, marks this explosive disruption. This is an airburst. The most famous modern example is, of course, the Chelyabinsk meteor of 2013. A 20-meter asteroid, weighing more than the Eiffel Tower, entered the atmosphere over Russia. It exploded at an altitude of about 25 kilometers with the energy of 500 kilotons of TNT. That's about 30 times more powerful than the atomic bomb that struck Hiroshima. The flash was brighter than the sun, and the event was a stark reminder of the power of these objects. The atmosphere absorbed the vast majority of that energy, shielding the ground from a direct, crater-forming impact. But even so, the shockwave that followed was devastating. What's amazing is that this visual spectacle can also be an auditory one, but in a very strange way. There are two types of sounds you might hear from a very bright fireball. The first is straightforward, a sonic boom. If a large meteoroid makes it deep into the atmosphere and explodes, it generates powerful shock waves that travel to the ground. But sound travels much, much slower than light, so you'll see the flash of the bolide, and then you'll wait. Depending on its altitude, it could be 1, 2, even 4 minutes later before you hear the delayed boom, a series of bangs or rumbles. The shockwave from the Chelyabinsk meteor was powerful enough to shatter windows in over 7,000 buildings, injuring 1,500 people, mostly from flying glass. These explosions also create infrasound, sound waves too low for humans to hear, which can travel around the globe and be picked up by special monitoring stations. But then there's the second, much weirder sound, electrophonic sounds. Witnesses to the brightest fireballs sometimes report hearing faint hissing, crackling, or buzzing sounds at the exact same moment they see the meteor. For years, scientists were baffled and often dismissed these as psychological tricks. How could you hear a sound at the same instant you see something happening dozens of kilometers away? The current leading theory is fascinating. It suggests that the turbulent plasma trail of a super bright fireball emits very low frequency, or VLF, radio waves. These waves travel at the speed of light, reaching the observer at the same time as the visible light. The theory goes that these VLF waves can then be transduced or converted into audible sound by objects in the observer's immediate environment. Things like aluminum foil, wireframe glasses, or even dry human hair could vibrate in response to the radio waves, creating a sound that our ears pick up. So if you ever see a spectacular fireball and hear a faint crackle at the same time, you're not imagining things. You're experiencing one of the strangest phenomena in atmospheric physics. For the vast majority of meteors, the journey ends high in the atmosphere, completely vaporized into dust. But for the bigger, tougher ones, parts can survive. The glowing, luminous part of the flight usually ends at an altitude of around 15 to 20 kilometers. By this point, the object has slowed down so much that ablation stops. It's no longer a fireball. It then enters what's called dark flight. It's no longer glowing, and it simply falls the rest of the way to the ground, pushed by gravity and high-altitude winds. It rapidly cools down. And contrary to what you see in movies, meteorites are not red hot when they land. The intense heat only affects a very thin outer layer, and the core of the rock has spent billions of years in the freezing cold of space. By the time it hits the ground, it's likely to be cool, or at most, warm to the touch. If a piece does make it to the ground, it officially graduates to being called a meteorite, and a fresh one will often have a very distinctive thin, dark, glassy coating. This is the fusion crust, the melted and resolidified rock from its fiery passage through the air. These meteorites are the ultimate prize. They are an absolute treasure trove for science. Why? Because meteorites are time capsules. They contain some of the oldest, most pristine material in our solar system. By studying them, we can determine the age of the solar system itself, about 4.568 billion years old, based on the oldest bits found in meteorites. They are tangible pieces of the planetary building blocks, showing us how planets like Earth formed from a disk of dust and gas. They tell us about the chemical makeup of the early solar system. To catch these falling treasures, scientists have set up networks of automated all-sky cameras around the world. When a fireball is spotted by multiple cameras, its trajectory can be calculated with incredible precision. From that trajectory, scientists can work backwards to figure out its original orbit around the Sun, linking a specific type of meteorite to its home in the asteroid belt or beyond. And citizen science is crucial. Organizations like the American Meteor Society rely on thousands of eyewitness reports to track fireballs, helping to reconstruct their paths and even predict where meteorites might have landed. From its quiet, ancient origin as a piece of rock or ice, a meteoroid travels for eons. Its final moments are a blaze of glory, a violent and transformative passage through our atmosphere. Each streak of light is not just a beautiful sight, it is a piece of cosmic history delivering itself to our doorstep. It's a reminder that we live in a dynamic, ever-changing solar system, and that the answers to some of our biggest questions about where we come from can arrive in a flash of brilliant, multicolored light. Thanks for tuning in to G Fun Facts Online. Join us next time as we explore another wonder of our universe.